Hello everyone, my name is Sanskriti Ranjan and I'm a senior majoring in computer engineering here at Clemson University. Currently, I'm pursuing research under Dr. Calhoun at his Future Technologies and High Performance Computing lab. Today, I'm going to give you a glimpse into our research in use cases of compressed cache simulator in high performance computing and quantum computing. High performance computing applications have been using data compression to reduce number of bytes that are transmitted or stored. Lossy compression algorithms help a user specify an error bounding metric such as absolute error or peak signal to noise ratio and help to ensure the accuracy of data. There has been work that has been explored in applying data compression at software levels to I/O and different checkpoints. For example, in 2017, Gordon Bell leveraged inline compression to double his maximum problem size and improve performance by about 25% in his earthquake simulation. On the other hand, caching helps keep data needed for computation in fast memory. It also helps reduce the data movement and thereby improve the I/O performance for distributed applications. Prefetching limits the delay in the critical path when the data is not found in the cache. Now, in quantum computing research, it becomes integral to use HPC systems and simulate the quantum circuits. This helps to understand the behavior of a quantum system and also helps developers to evaluate complexity of these quantum algorithms. Now, if you look at a quantum system, one requires 2 to the power n amplitudes for representing n qubits. Now, if we look at it from the perspective of how these amplitudes are represented, we require at least double precision floating point data points, and we require one for the real and one for imaginary. Therefore, for n qubits, we end up requiring 2 to the power n plus 4 bytes of data. Now, this keeps increasing exponentially as the number of qubits increase. Therefore, it becomes important to help reduce the memory footprint because the size of the quantum circuit simulation would be limited by the capacity of the classical HPC system. Now, to reduce the footprint in memory, we utilize data compression, which helps us to determine how large the quantum system can be on a same memory capacity classical computing system. Frank Capello, in his paper on full state quantum circuit simulation, shows that through data compression, we can reduce the memory requirement of a 61 qubit Grover search algorithm quantum circuit from about 32 exabytes to 768 terabytes of memory. Now, all these high performance computing and quantum circuit applications, they require compressed arrays. And these compressed arrays are always stored in caches so that they can be accessed quickly. Now, it becomes important to understand how these caches will affect the runtime of high performance computing or a quantum computing application. Caches of different sizes and different policies, such as set associative or a direct map cache, will definitely impact not only the runtime performance, but also the temporal or spatial locality. And this thereby has an effect on the memory access pattern. Now, on the left, as we can see, a stream application and how its bandwidth gets impacted based on the type of cache that is used. And we also see in a matrix-matrix multiplication how the size of the cache impacts the runtime performance of the application. Now, quantifying these memory access patterns and the amount of data locality, we need a proper baseline that will help us compare all these software caches. Therefore, in this project, we want to build a cache simulator which will help us model the hit rate and miss rate for all the arrays of different applications, and therefore understand how it will impact the runtime performance for these applications. So in our simulator, what we basically do is we model the performance, and a user will input the cache size, the policy, and also the dimensional of the specific application that he wants to test. Now, once he has been able to input all these inputs, we will run the simulator for the policy and the size and see how it impacts the hit rate and the miss rate for that specific cache. This can be compared for different dimensions, as multidimensional blocks are really important for software compression algorithms today. Now, this data will help us understand how to improve an application's memory utilization or its runtime performance, as the simulator will help us gauge from the different cache sizes and different policies what is to be changed or modified. Now, this tuned version based on a specific cache size and policy can then be run on different architectures to determine the performance portability of that application. And now this catalog of data can be used to validate our cache simulator and thereby help in improving the runtime performance of applications. Through this characterization of memory access patterns and how it impacts the runtime performance, we can further explore different optimizations such as vectorizations, compressed memory implementation, and then go on to comment on their viability.